So a lot of chemistry is oxidation reduction chemistry to get to what we finally want in the end. All right, let's go ahead and get started. So we're going to start out with the reaction that we're going to learn the mechanism of later on in the semester, all right? So we have a whole chapter on carboxylic acid derivatives. So I'm just going to introduce you to the 2 P's of this for now, and then you can learn the mechanism going forward. All right, so this is going to be learning objective 16J, and this is the 2 P's for the formation of esters. So we'll talk about that functional group. You should have seen this before, but we're moving away from how to form aldehydes and ketones and carboxylic acids, and we're thinking about making esters. We're going to make esters from alcohols and carboxylic acids. So this reaction is sometimes called the Fischer esterification. I, as you know, prefer describing it based on what's going on. If you're following along in your book, this is 16.8. All right, so let's talk about this formation of esters. So esters are used all the time in chemistry. So you may know the cloth fabric polyester, right? This is many esters. Esters are also really big components in fragrances. So if you have perfume or your shampoo smells really nice, there's probably an ester responsible for that. All right, so we're gonna take an alcohol. So R is gonna be some carbon-based group, as we've always seen. And this alcohol is gonna serve as your nucleophile in this reaction. We don't need to know what is the nucleophile and the electrophile because we're not doing the mechanism, but I just like to prepare everyone. So when you see this later on, you're going to be able to know that that's the alcohol. All right, we're going to have a carboxylic acid. All right. And this would be your electrophile. So carboxylic acids, I've drawn this, what we would sort of call the, classic carboxylic acid in this reaction. But we can have other groups other than this OH here. This can be other leaving groups. That's going to be a component of an entire chapter that we're going to learn. So today I actually decided to take that out so that we could simplify it down a little bit. But that can be a chloride, it can be an acid chloride. We've seen those before. It can be other groups there, but for now, we'll just learn this from carboxylic acids. So we're going to do this under 2 sets of conditions that are catalytic, all right? So we can have 2 catalysts. So we can have H2SO4, which would be an acid catalyst. Or we can do this reaction with a base catalyst using pyridine as a base. Using pyridine and H2SO4 as representatives of acids and bases. So if you recall, the structure of pyridine looks like this. And this lone pair on the nitrogen of pyridine can act sort of as the base or a nucleophile in this reaction. So we have a couple conditions that we can do this under. We're going to have an entire lecture on talking about functional group tolerance and why you would want to use one versus the other. But this is often you need to use one versus the other because of other functional groups that are in your molecules. Okay, so what do we make in this esterification reaction? Well, you guessed it, we make an ester. And so the bond that we make is going to be this carbon-oxygen bond from our alcohol to our carboxylic acid, and this is an ester. It's always very important to understand, what our byproducts are, because this can help us a lot. And in this reaction, we've just lost water. One of those H's came from our alcohol, and the OH came from our carboxylic acid. So sometimes it's a little bit hard to see when you have an OH in your both your starting materials where it came from, but we can consider what is going to react as the nucleophile in this reaction, and that's the alcohol. And so that's why we're keeping that alcohol. That's what's going to make the bond. All right. So, another thing that I want to note here is actually this reaction. When we think about it specifically with H2SO4, is actually a reaction that requires equilibrium arrows. So, actually, we're going to draw this to have equilibrium arrows. All right. So, this reaction is reversible. So oftentimes when we have equilibrium arrows, we don't really pay attention to them because oftentimes they're in the mechanism of just one step. We've had one instance where equilibrium arrows really made sense to include and to emphasize, and that was when we were doing sulfonation. We had two sets of conditions. One set of conditions was related to using SO3 as a very strong electrophile, and it was not a reversible reaction, versus when we used H2SO4, it was a reversible reaction. So, when we're thinking about the bond strengths here, one side is not really favored over another, all right? And so when this reaction is reversible, that means that water would come in and act as a nucleophile. And reverse the reaction. That's another reason why it's good to have byproducts drawn in a reaction. All right, so the reaction is reversible, so we need to think about how we can, drive the reaction forward. We don't really want a reaction that's reversible because maybe you only get 50% of your product and then you're stuck with 50% of your starting material and you have to separate that out. Actually, in 2311 lab, you do this reaction, you do an esterification reaction, and you do not get your reaction to go to completion. All right, so how would we drive this reaction forward? This goes back to Le Chatelier's principle. So our next learning objective is 16K. And this is to explain how Le Chatelier's principle can drive the reaction forward and favor the products of Fischer esterification. So this is an explanation of equilibrium concepts. I'm going to put that in parentheses, equilibrium. So in this case, we're talking about Fischer esterification and these esterification reactions, but actually Le Chatelier's principles comes in equilibrium, comes in all the time. We'll talk about removal of water and things like that many times throughout this class, and these same concepts will apply. So we don't have to silo ourselves into thinking about it just for esterification reactions. All right, so when we're taking a look at equilibrium, what we're looking at is the amount of compounds in the starting side versus the amount of compounds in the product side. So as we remove products, we can get the reaction to go forward, or we could add more starting materials and get the reaction to go forward. So those are the two concepts. So we can push the reaction to products by adding excess alcohol, or carboxylic acid. So in this case, this is the starting materials. And this will push equilibrium to the right, giving more product. Right, so if you were to do one-to-one of everything in this reaction, you get this equilibrium that's kind of in the middle. But if we start to add one or more of our extra components, so say we use alcohol as our solvent, we have so much alcohol that it's going to outcompete the ability of water to drive the reaction in the reverse direction. All right. The other thing that we can do is we can remove, number 2 is we can remove the water. So remove the products essentially. And this also pushes equilibrium to the right. Towards the products. All right, so it's quite easy actually to remove water. We use the piece of equipment that we use is called, it's named after the person. It's called a Dean Stark trap. Yes, it is not Tony Stark trap, but yes, you can remember it that way. So Dean Stark, I don't know who Dean Stark was, but apparently they figured out that you could add this piece of lab equipment. And basically there's a picture on page 650 in the textbook. You could just Google it though. So basically what this does is this collects your water through distillation. Right? So you're going to distill, you're going to have your reaction refluxing, which means heated to past the boiling point, and the solvent is going to vaporize, and the water is going to vaporize in the reaction, and then it's going to condense, and then it's going to funnel the water into a different part of your piece of lab equipment. All right? So basically a Dean Stark trap just gets rid of water in your reaction. All right? So that's what we can use. You could put that over the arrow in your reaction to drive it forward. So I'll show you an example of that. So we might have this sort of cyclohexyl alcohol here. And then maybe we have just benzoic acid. And then over the reaction arrow, this would normally be at equilibrium, but we're not going to draw it there. We're going to take an acid catalyst, we'll add a little bit of heat to this so that distillation happens, and then we can use our Dean Stark trap. It collects water on the other side, and then that's why we no longer have those equilibrium arrows. Instead, we just have our product and we've removed water. I'll indicate this is removed. All right, so the solvents we typically use with this, benzene, or toluene, which I'll draw that out for you. That's just benzene with a methyl group. Right, we typically use benzene or toluene solvent in this reaction. And this is a practical reason. So benzene and toluene are pretty high boiling point solvents. So when we boil them, we also kind of get close to the boiling point of water. There's also something that happens, this is just an FYI, I think this is a cool concept, but there's something called azeotrope, which is a combination of two solvents together. And when we combine those two solvents together, their intermolecular forces lower the boiling point of both of the solvents. And so you can run this reaction with less energy, and water forms a really great azeotrope with benzene and with toluene. So that's just like a fun fact about azeotropes. The very first reaction that I ran in the research lab when I was a freshman in college used a Dean Stark trap. So I personally have used this dozens of times, and it was my very first reaction. All right, so that is an esterification reaction. We've now learned how to make an ester, which is pretty cool. So when we think about an ester that has a lot of bonds to oxygen, right? It has a carbon-oxygen double bond, it's a carbon-oxygen single bond. And so we're going to talk a lot about carbon, oxygen, multiple bonds and how to form them. We've already figured out how to reduce them, but let's go ahead and see if we can figure out how to form them. So we're going to have two learning objectives on this slide. So this is going to be learning objective 16L, which is the two P's of formations of aldehydes and ketones through oxidation of alcohols. So no mechanisms here. But we're going to learn how to oxidize alcohols and form aldehydes and ketones. We've learned reductions before, but these are oxidations of alcohols. All right, so in an aldehyde or a ketone, we have two bonds between the oxygen and carbon. Our next learning objective is almost the exact same. Instead of forming aldehydes and ketones from alcohols, we're going to form carboxylic acids from alcohols. So that's learning objective 16M, which is the two P's of formation of carboxylic acids through oxidation of alcohols. And these are all in chapter 16.9. All right, so before I said an aldehyde and a ketone had a carbon-bound double bond, two bonds to oxygen, carboxylic acids, higher oxidation state, they now have three bonds from carbon to oxygen. All right, so let's go ahead and see what this looks like. All right, so we're gonna have an alcohol here, and in this case, we're gonna have a primary alcohol. And generally I don't draw in hydrogens, but in this case, I'm going to be pretty suggestive to you. Right, then we're going to do, this is the sign or the symbol for oxidation. So this is an oxidant that we've added. And we'll talk about what those chemicals are. And when we oxidize, we can go ahead and we can form an aldehyde. All right. And this is that first learning objective, 16L. You can go ahead and keep going further with a stronger oxidant or more equivalents of our oxidant. And then we can form our carboxylic acid. This is learning objective 16M, right? We had two listed on the top. So we have options to stay at the aldehyde or keep going to the carboxylic acid. All right, so it kind of depends on the structure of our compound, whether we can do this. So very suggestively, I've drawn this as a primary alcohol. And we've lost both CH bonds in order to make more bonds to oxygen. So we broke into CH bonds and we made two extra CO bonds, all right? If you have a secondary alcohol, we only have one hydrogen. All right, so that means that we can go ahead and make a ketone from this reaction. We can oxidize off that one CH bond. We can form a ketone. But there's no more CH bonds to oxidize, so no reaction if we add more oxidant. Okay, no CH bonds. So can't oxidize to the carboxylic acid. Right, So we have to be really careful with the identity of the alcohols we're trying to oxidize to see how far we can get. Let's keep going here. Let's see if we had a tertiary alcohol. We'll have R1, 2, and 3. And if we go ahead and we add in an oxidant here, no reaction. Right? There's no CH bonds. So can't oxidize. Right? So this is the difference between a primary alcohol. We can go all the way, get rid of all those CH bonds, to our secondary alcohol. We can make it into a ketone, but we can't make it into a carboxylic acid. And a tertiary alcohol, which that's never going to change, right? We can't have 5 bonds to carbon. We have no CH bonds to lose. So no reaction. All right, so, it's a 2P question. So we want to know, what is the oxidant? Right, so what is the identity of this bracketed O? All right, so we use a lot of chromium 6 reagents. All right, let's look where chromium is on the periodic table. It's the first row transition metal in our D block. It's element number 24. And it's very strong at oxidizing. So this number here is the oxidation state of the metal. We see that it's a very high oxidation state, chromium 6. We lost 6 electrons here. So it's a high oxidation state, so it's going to be a strong oxidant. All right, plus we're going to need a little bit of help too with acid. All right. Okay, so the reagents that we can use are going to be potassium 2, chromium 2O7. Right, plus we need a little bit of H2SO4, plus we need a little bit of water. Right, in our solution, this is what we add in. And when we add this in, what we form at the end of the day is chromic acid. This is our chromium 6 oxidation state. And that's what we form. Right, you can use another set of conditions that you can use, doesn't matter, is the sodium salt of this. It doesn't have to be potassium, it can be sodium, depends on what you have on hand in your lab. And the sodium still requires H2SO4 and water. It goes the same thing. The chromic acid. Or there's something else that we can use, which is this chromium oxide. All right, so there's a lot of chromium 6 reagents that will do this reaction. All right, these are strong oxidants. And they will oxidize as much or as high up as possible. Question? It does not. Yeah, great question. So the chromium oxide does not need H2SO4. Yeah, so it ends up being chromium 6 as well, and it's double bonded to each of those oxygens. Right, so they're strong oxidize. They will oxidize as high as possible. In oxidation state. Right, so if you want to get an aldehyde out, you can't. It's just going to go forward. It's a non-selective reagent. So what does that mean? it means that if we have an alcohol that's primary, and we add in a chromium 6 reagent, it will go through the intermediate of an aldehyde. And no matter what, it just keeps going to your carboxylic acid. Carboxylic acid is the only product. I always get asked questions about stoichiometry here. Wish we could stop it, but it does not. It goes through the aldehyde, but we don't observe it. We have other tempered reagents that we can stop at the aldehyde, but with chromium 6 reagents, going all the way. Or I should say with these chromium 6 reagents. Chemists are really good at figuring out how to get around things. So we develop a lot of new methods. All right, so these are great reagents. If you have an alcohol and you want a carboxylic acid, great, we can get there. All right, so recall what this means is that we can't stop there. So let's go ahead and do a couple of chime-in questions, all right? I'll give everyone, I see a few people still writing. So go ahead and start to get out your devices, and I'll open the chime-in question once I see people stop writing. Okay, so we are on lecture 11 already. Can you believe how much chemistry you've learned? Okay, so let's take a look at this. Which compounds below can be oxidized to which of the following functional groups? All right, so the first thing we should check for ourselves is, we said that chromium reagents and excess oxidants and things like that will oxidize as high as possible. So then we need to check, is this a primary alcohol, a secondary alcohol, or a tertiary alcohol? Right? Looks to me like a secondary alcohol. So even if you have a really strong reagent like chromium, it'll go as high as possible. It has to stop if there's no CH bonds. All right, so let's see what people are thinking. All right, great. I'm loving this distribution of answers. So I see why people said aldehyde. It is 2 bonds to carbon, so it's very close to the functional group. And aldehyde does have a hydrogen on it. This has 2 carbon-based groups. And I see that, even though it's not a trick question, it's a very fair question, but I see that people didn't automatically say we're going to the carboxylic acid. Instead, they said we have a secondary alcohol. Let's stop at the ketone because that's all that we can do. So I think that's awesome. All right, so we'll do one more question. So don't put your devices away. I'm just gonna, haven't seen anyone else answer a question for a bit. Okay, so let's close this question and let's see what we think about the next question. Right, which set of reagents would result in the following transformation? Yep, I realized that I should have taught the sworn conditions first, but give it a go. See what you can do. I also think I was incorrect. I think chromium oxide apparently does need H2SO4 and water. So I was wrong. Thank you for asking that question. I'll write that back in the notes. Yeah, so I'm sorry, I asked this question out of order. I should have asked it later on in the lecture, but we're just going to go with it. These are not based on correctness anyways. All right, I see we have the same number of participants as we had before. All right, I'm loving that people are knowing that we need those strong oxidants. So even though we haven't learned these other oxidation conditions, you've identified the 3 sets of conditions that we can use. So I think that's great. All right, so in the 10-10 section, these will be asked in the right order. All right, so let me close this question. Okay, great. So kind of summarizing our chime-in questions that we have. In our first example, we had a secondary alcohol. All right. So in that chime in question, everyone did a great job of saying, no matter what the oxidant is, we're always going to go to the ketone if we do not have a primary alcohol. All right, and the other thing is, so let's go back and correct my error here of chromium O3. This does need H2SO4 and water. So yeah, go make that adjustment in your notes. All right, and then the second chime in question. So this was chime in 1. Chime in 2 was asking us that we needed strong oxidants with chromium 6 to go all the way to the carboxylic acid. All right. So what if we don't really want to go to the carboxylic acid? Say we want an aldehyde or a ketone. Is there a way that we can do that? Well, we know the ketone we can get to from using whatever we want because it can never further oxidize. But what about our aldehyde situation? All right, so how do we stop at the aldehyde and not fully oxidize to the carboxylic acid? How are we going to accomplish this? All right, so this is going back to, I just needed to pull up the learning objective number. So this is still part of learning objective 16L, which is the formation of aldehydes and ketones. So this is just that learning objective continued. All right, so we have a couple of sets of conditions that we can do. If we have a primary alcohol, we can use a reagent called PCC or PDC. All right, and this will get us to our aldehyde. All right, so the key to this reaction conditions are that there's no water. All right, so key is no water with reagents. All right, so we need some water. We don't need to know the mechanism, but we do need some water to turn into the carboxylic acid. If we have no water, we're not going to turn into the carboxylic acid. All right, so PCC, if you wanted to know, is pyridinium chlorochromate. PCC. I know acronyms are really frustrating to students. And so pyridinium is a very weak acid. And chlorochromate is ClCrO3 minus. The pyridinium chlorochromate. So no water in this reaction. We cannot turn into the carboxylic acid because there's no water. All right, PDC is just a very close derivative of this, which is pyridinium dichromate. Right, and so this is the same pyridinium and Cr2O7 2 minus So we need two equivalents. Let me draw out your pyridinium. We need two equivalents of this to balance that out. And again, no water in these reactions. All right. So I've drawn an aldehyde here, but we can also use for secondary alcohols to make ketones, right? We could use any of the reagents that we have to make a ketone, right? And a secondary alcohol. You could just add this to the list of the many things that oxidize secondary alcohols to ketones. But usually when we're using PDC and PCC, it's for a reason. And the reason is that we're using a primary alcohol. All right, so unfortunately today is a lot of like memorizing reagents, all right? So I know that's a big part of OChem that people don't like, but here we are. So a lot of chromium reagents will be able to oxidize to a carboxylic acid, and your sort of key is if there's no water in them, then maybe it's gonna be a PCC or PDC. All right, so we have a problem with chromium, all right? It's highly, highly, highly toxic. So we're gonna continue learning objective 16 L, continued again, and I'm gonna give you a much greener way to do an oxidation. All right, so chromium is toxic. So we don't really like, I mean, most chemistry is reagents have some safety concerns, but in this case, we're going to get a stoichiometric amount of chromium at the end of the day, and we really don't want to dispose of that. So an alternative is called the Swern oxidation. Right. Rarely do I like to use names of reactions, but there's so many conditions in the Swern reaction. This is the one that I generally would just call the Swern reaction. All right, so we start from a primary alcohol, right? We're still trying to make those aldehydes without oxidizing too much. So we need these two CH bonds. All right, and our conditions, you see my arrow is getting really long. Are these reagents called DMSO. This is called, you don't need to know the names of these. That's dimethyl sulfoxide or DMSO. This is oxalo chloride, which is Cl2C2O2. We specifically use dichloromethane or methylene chloride. Those are two names for the same thing as our solvent. This is run cold at minus 50 degrees Celsius. And then we have a second set of conditions too. After all of this is done, then we are going to add in triethylamine as a base. And the product that we get to is our aldehyde. The byproducts of this reaction, where does our oxygen come from to oxidize our aldehyde? It comes from the DMSO that we added in, which turns into dimethyl sulfide. We lose CO in this reaction. We lose CO2 in this reaction. And then we lose a proton in this reaction. These are our byproducts, all right? The takeaway is, though, if you were to list Swern conditions over your arrow, I would be okay with this. All right, so the takeaway is primary alcohol to an aldehyde using the Swern conditions. This is a very infamous reaction in labs because if you look at these byproducts, you may or may not know that dimethyl sulfide is the smell of rotten eggs. So if you run this reaction in the research lab, you generally run it at night when maybe only your safety buddy is around, because it drives everyone out of the lab because it smells like rotten eggs. But you don't have to be exposed to chromium toxicity, so trade-offs. All right, so these are the conditions that we have. So I know this is a lot of content, but I'm going to go ahead and stop the lecture and give you 5 minutes back because I didn't want to go into any more content. This is already like enough content. So yeah, go ahead and start getting comfortable with these primary alcohols versus secondary versus tertiary. Get comfortable with how much those can oxidize, and then get comfortable for primary that the carboxylic acid and aldehyde are two options depending on the reagents you use.